Achieving Greatness in High-Impact Weather Operations. This video is brought to you by the Rain Snow Line. When you forecast a foot, but you just get an inch, the Rain Snow Line. By the once-in-a-100-year flood. You know, the one that occurs every few years or so. The once-in-a-100-year flood. And by freezing rain. When descending down an icy bridge, hit the gas, then slam on the brakes for the adventure of a lifetime. Freezing rain. Hi, Pete Wolf here with an interesting topic, one you generally don't get in forecaster training. This is one that's more personal in nature. I usually provide training videos on science or technology, focus on equations or graphs or statistics. This is going to focus on achieving greatness in high-impact weather operations and acquiring the high level of satisfaction and fulfillment that comes with that. In this video, I'm not going to focus on failure. Failure is simply a learning step towards future success. I'm going to focus on 3 levels of achievement in operations: greatness, goodness, and satisfactoriness, for lack of a better word. So satisfactoriness refers to achieving the mission and nothing more. It tends to be associated with a low risk of failure, but also a low level of satisfaction as a result. So for example, radar shows a clear severe storm signature. You issue a warning with 5 or 10 minutes lead time before severe weather is reported. That's an example. You've met the mission by issuing the warning. The mission doesn't necessarily require additional statements or DSS messaging. You achieve the minimal mission requirements. Goodness is where you exceed those mission requirements, but without overextending risk of failure. So you have a little higher risk of failure, but also could gain a more moderate level of satisfaction as a reward. So in this example, based on radar trends, you issue a warning before the storm becomes severe, or in a case where you have a warning out already, you issue the next warning downstream before the hazard exits the first polygon to provide additional lead time. Those will be examples of goodness in operations. Greatness is where you utilize science and technology to greatly exceed mission requirements while properly managing risk. And that's important because it tends to be associated with a high risk of failure in order to achieve a high satisfaction as a reward. So in this example, you would accurately and precisely target a threat message well before the hazard even develops, maybe with an hour or 2-hour lead time, as well as to chat precise hazard locations with each radar scan, providing more focused threat information than you can get from WarnGen. Those would be examples of greatness in operations. Here's an example of a chat following a potentially tornadic storm, scan by scan. These achievement categories directly relate to personal satisfaction and fulfillment. There's no greater feeling than when utilizing science and the tools and technologies we have to hit an event, especially before radar shows the hazard. It can be really satisfying. Unfortunately, the categories also directly relate to risk. You cannot have large reward without having substantial risk that accompanies it. You also cannot minimize risk without minimizing reward. They go hand in hand. In addition, the categories directly relate to the amount of effort and the difficulty of the effort needed to manage that risk in order to achieve a high level of satisfaction. Does this mean you have to choose between great success and reduced risk of failure? No, not necessarily. There are steps you can take to try to manage risk in order to achieve a higher level of satisfaction, and we'll discuss this shortly. Here's a severe weather example. Let's say you have a squall line moving in, you have a circulation, a mesovortex along the line. Satisfactoriness would be issuing a large polygon along that line for the potential for 50 to 60 knot wind gusts. So the warning alone achieves the mission. Thus, that achieves satisfactoriness. And the radar is basically responsible for what happens. If you have an event occurred that was not warned, well, it likely was because the radar didn't show a signature. So this would be an example of satisfactoriness. Goodness is where you go beyond the basic warning and issue updates, maybe in SVSs or DSS messaging, perhaps focused on the circulation itself, where the worst is likely to be. Greatness is where we go beyond the warning, perhaps providing pre-warning information with longer lead time further downstream given a similar environment. So we might use partner chat or social media graphics to provide 1 to 2 hour lead time expectations downstream of the hazard. Here's a flood example, and this is how a flood event may typically play out. So you have heavy rain, maybe training of convection over the same area. Radar rainfall estimates show rain amounts piling up 3, 4, 5 inches. We get above flood guidance, and so you issue a flash flood warning. Maybe an hour later, someone in the office calls the affected counties and gets reports of water over roads, which is then LSR'd with an hour lead time. That's great, right? And yet it doesn't feel necessarily that satisfying because radar rainfall estimates don't forecast rainfall. They show the estimated rainfall that's already fallen and likely leading to flood initiation. So the reality is you may not have had any real lead time on the warning. Thus, it's not terribly satisfying. Goodness, as you might be able to guess, is trying to recognize the developing training pattern and to get the warning out before rainfall reaches flood guidance numbers. And thus you're trying to get lead time before flooding initiates. Greatness would be utilizing science and technology to recognize environment clues for the setup of the training pattern before the heavy rain even develops, maybe an hour or two in advance, targeting a flood message scaled down to the likely threat area. I've been able to accomplish this a few times. It's amazingly satisfying, but it's also amazingly difficult. And there is, of course, risk associated with that, risk of being wrong. But this is where greatness would be achieved. There are obstacles to achieving goodness or greatness in high-impact operations. I'm going to refer to 3 of them: lack of knowledge and experience, fatigue, and fear. Knowledge and experience are important unless you have psychic powers, which I don't have. But it's not for a lack of trying. It just hasn't worked out for me. And I'll demonstrate that to you very quickly here with a deck of cards. I'm just going to shuffle them a bit, and let's see what happens. Four of clubs. I didn't even get the color right. So, without psychic powers, you're left with knowledge and experience to build. Then there's fatigue, an unfortunate reality that exists in the Weather Service, which we'll get to. And then the big one, fear. So without psychic powers and without being born with all the knowledge you need, well, that requires building knowledge and experience over time. It's important to understand the sounding and the hodograph, to understand storm environment and how that relates to what you're seeing on the radar, as well as understanding the issues associated with radar data so that you interpret the data correctly and can recognize potential error. This is important for achieving greatness in operations. Fatigue is a reality in the Weather Service, and it's mainly because of how we operate. We have 115 CONUS WFOs across the country with 15 operational meteorologists, including operational managers in each one. And if you do the math, that's over 1,700 meteorologists. An amazing resource, probably 4 or 5 or more times what a similar weather organization with national reach would have. And the reason for that is because it's an expensive resource, costing in the neighborhood of $150 million a year, which the private sector can't possibly afford. So it's a great resource that we could utilize if we operated as a national weather service. That would mean no rotating shift works, and it would not require long hours. So we would be able to minimize the impact of fatigue. However, we actually operate as 115 weather services, each with 15 operational METs. And to provide 24/7 operations in that approach requires rotating shift work, and it can require long hours, making fatigue a reality. In addition, how do we deal with high impact events, such as a severe weather event in the Southern Plains? You might have 4 or 5 WFOs impacted, so they're dealing with an overwhelming amount of work. They have to call in extra people on overtime, work long hours, and that all leads to fatigue. Meanwhile, you have 50, 60, 70 offices where the weather's quiet doing their own thing. So we don't share the work amongst many offices, and thus a few offices end up with fatigue. The problem with fatigue is that a tired brain cannot interpret data the same way that a fresh brain can. Subtle changes, say from scan to scan, might not be picked up, as in this example where we have a little weak echo notch rotating around the southern end of a developing storm with tightening rotation where that's occurring, likely imminent signs of a potential tornado. A tired brain might not even see this. I know in some events I've worked where I've missed a few occurrences of severe weather, I go back the next day when I'm more refreshed and look at the archive data, and I see signatures I swear were not there in real time, but there they were in the archive data. It's a reality that the tired brain just cannot interpret data the same way as a fresh brain. So, given the reality of fatigue, what can we do to lessen its impact? When it's possible, if you have a service backup office not involved in the event, see if they can help with some of the other duties so that you can focus just on the event itself. It's important to rotate the radar or warning person so that they're on the radar no more than 4 consecutive hours or so at a time. Now, when you're dealing with really high-end severe weather and very clear signatures, you probably can go longer than 4 hours. In the case of more marginal events like what we see in Florida most of the time, where we have marginal signatures, that can tire the brain pretty quickly, and maybe even less time would be better. The big one is fear. Now, unlike fatigue, which is an all-around bad thing, there's nothing good about fatigue in operations. Fear is actually a good thing. It helps us keep our risk-taking in check. It helps us balance risk and reward. It keeps our mission in focus and helps us question the data, make sure we're making good decisions, and also communicating information better. However, when fear starts to dominate our decision-making process over science, well, that's when it becomes a problem. So you've likely heard this statement: it's better to issue a warning and have nothing bad happen than to have no warning out when something bad occurs. This is a statement of fear. Better safe than sorry. I don't really prescribe to this kind of statement. I prefer this one. Better to issue a warning when something bad happens and issue no warning when nothing bad happens. This is a statement of achievement. It's harder, it involves more risk, but it involves much greater satisfaction in operations. Perhaps one of the most difficult decisions in severe weather operations is having radar detect a storm with rotation and deciding not to issue a tornado warning. That's a hard decision because if something bad happens, there it is on radar, you have rotation, and how do you defend yourself for that? It's a very difficult decision. However, we don't want fear to rushing us to that judgment. We want fear to get us to question the data, make sure it's accurate that we're basing our decision on. Is that rotation co-located with the updraft, as would be the case when you're ingesting streamwise vorticity? Or would it be along the edge of the updraft in the case of crosswise vorticity? Is it accurate data, or it might be bad data associated with, say, with side load contamination? Is it an actual deep circulation, or is it just an enhancement along a shear axis? This is what we want fear to do to help us make better decisions. Speaking of radar, let's turn to this topic for a moment. Radar sends out a pulse of energy and listens for small amounts of energy that's scattered back to it from distant targets. And from that small amount of energy returned to the radar, we get all kinds of information. Reflectivity structure, velocity data, hail spike and TDS signatures, bad winds, and so forth. It seems miraculous we get so much from so little. You'd think there'd be some kind of a catch to this, right? Well, of course there's a catch. And the catch is that what radar provides is a seemingly realistic view of its reality, not necessarily the actual reality. And that's due to a number of radar-based issues which become more prominent the further away from the radar you get, such as the interpolation that occurs between elevation slices, the increase in beam width and height with distance, the impact of beam refraction, velocity data that only shows the radial component, and so forth. So you might have a situation like this where radar suggests a bounded weak echo region, and that may very well be the case. Or it could be a mature cell right next to a dissipating cell, far enough from the radar with a widening beam that it may look like a B-word, but may not be. This leads to an interesting question. Why does fear lead us to focus on radar data when the data could be erroneous or misleading? And I suspect the answer to that relates to the training we received over the past few decades. Really focused heavily on radar. In fact, when I was a forecaster a long time ago, when Doppler radar first came out, the training was focused almost exclusively on Oklahoma supercells. And then we learned later on there were QLCSs and pulse storms and other things we had to understand. But training was focused almost entirely on radar-based warning decisions. More recently, we're getting more and more training on storm environment and that type of thing. But in the past, it's predominantly been on radar. So our dependency has tended to be on radar. Another question is this: what percentage of convective warnings are actually issued for non-severe or non-tornadic storms that simply appear severe or tornadic on radar? And there's no way to know the answer to this for sure. but my suspicion is it's probably greater than 50%, just based on the FAR scores, particularly for severe thunderstorm warnings. Already near 0.5, despite the fact that a number of warnings, especially here in the southeast, are verified with a single tree down or something that may be caused by sub-severe winds. So let's talk about warnings now. And a common topic of warnings deals with false alarms. I looked at a 5-year period from January 1st, 2016 through January 1st of 2021. And our performance management website indicated for that 5-year period our national tornado warning false alarm rate of around 0.70. I've always had a problem with this statistic because it doesn't penalize for warning size. In other words, if every tornado warning was the size of the United States, our FAR would still be 0.70, and that rubs me the wrong way. So I'm going to focus on this from a warning area perspective. During the 5-year period, we had 11,960 tornado warnings. Our performance management website indicated an average polygon size around 294 square miles. So if you do the math, you come up with a number just over 3.5 million square miles. That sounds huge, right? Well, to put it in perspective, the area of the continental United States from coast to coast is in the neighborhood of 3.1 million square miles. So we're talking about, 1 1/8 CONUSes for tornado warning area over that 5-year period. I want to compare that to the actual area struck by a tornado, or very close to being struck. We had 6,926 tornadoes. And given my graying hair, I really don't have time to look at each of the 6,926 tornadoes to calculate area for each one. So I'm going to approximate just for illustration here. And I'm going to use 3 square miles. How did I come up with this? So tornadoes on average are very small, less than 1/8 of a mile wide, maybe 3 to 5 miles long on average, maybe less than that. And then I want to add a little buffer area close to being struck. So I add a 1/4 mile on either side of the track and maybe another mile or 2 along the track. So I'm going to go with about 1/2 mile wide and about 6 miles or so long. And that gives me 3 square miles of area struck or very close to being struck. Now, it turns out it doesn't really matter if you use 2 or 4 or 6 miles. It's not going to change the end result that much. The total tornado area comes up to 20,778 square miles. Now, the area of Ohio, that state, is about 40,000 square miles. So we're talking about the area of half of the state of Ohio compared to 1 1/8 CONUSes warned. As a result, the way I compute false alarm rate using area is I take the total area warned, I subtract the area struck or close to being struck, which combined is essentially the area warned that's not struck or close to being struck, and divide that by the total area warned. And I come up with about 0.994. Very different than 0.70. So is the problem that our warnings are too large? What if somehow science and technology would allow us to reduce warning area by like 2/3 to just 100 square miles? Now, uncertainty and data error and so forth really can't allow this as an average of all tornado warnings. But let's say we could somehow. Would that be a big deal? Would that really reduce the false alarm problem? After all, we're talking about removing 2 million square miles of warning area from the 5-year study. Surely that has to add up to something. Sadly, no. If we look at today's approach, 3 square miles struck or nearly struck divided by 300 miles warned, that gives us 1%, or again, around 0.99 for a false alarm rate. If we could reduce that area to 100 square miles, it raises that percentage all the way up to 3%, or an equivalent FAR of 0.97. That is incredibly disappointing for that amount of change to have so small an impact, seemingly. There's still a problem as far as false alarms, and this is due to the fact that tornadoes are small and brief and very rare. So even with the small polygons, you're still rarely going to see a tornado, even when you're under a warning. For me, I've been under over 50 tornado warnings in my lifetime. I've only seen 1 tornado, and I had to drive to see it, although it was still under the polygon, so it still counts. So my own personal false alarm rate is somewhere around 0.98 or 0.99. And I suspect that's the case for most people. Most people never see a tornado or may see it once in their lifetime. I also looked at the legitimate warning concept. This basically means that if a mesocyclone, if rotation is going over my house, it's your job as part of the mission to let me know that I'm in danger, that there could be a tornado. Whether a tornado occurs or not is irrelevant. If there's danger, the job is to notify me of that. So if I use, say, a 30 square mile average mesocyclone track, and I use that as my area affected, I can come up with an FAR around 0.90. A little better, but still very high, much higher than the 0.70. So what average polygon size would I need to be able to reduce the false alarm rate down to the 0.70 as we calculate it? Turns out to be a very tiny size. In fact, if you use 10 square miles, that's 2 miles by 5 miles. If you use that for all warnings, including the majority that don't have a tornado associated with them, you come up with about 0.83. It's only if you utilize this with just verified tornado warnings where you have tornadoes that it brings it down to 0.70 in terms of area. 10 square miles is awfully tiny. We can't provide detail in terms of threat and impact in that type of scale. Or can we? Don't get ahead of me, that's coming soon. Lead time is another common topic on warnings. A 5-year study showed a tornado average warning lead time around 8 minutes, which in and of itself is probably enough time to take protective action. The problem is that not all of our warnings provide at least that much lead time. In fact, this chart of lead time cases is missing 2,700 zero lead time tornado cases. Social scientists have studied this and suggest a more favorable average lead time around 30 minutes, which is the orange dashed line. And as you see on the chart, only a small percentage of warnings meet or exceed that value. The problem I have with both of these is that they refer to kind of a one-size-fits-all approach, and I don't agree with that, because there's a variety of need. Just as there is a variety of customers, the need has considerable variety. When I'm at home, I only need a couple minutes to take protective action. If I'm taking a walk down the street, it takes me 5 or 10 minutes to get back to take protective action. Getting school students or business workers to shelter might take 10 minutes or so. Getting mobile home residents to a sturdier shelter ahead of a tornado might take 15 or 20 minutes. Finishing a task at work or at the store, and then driving home so you can shelter with family could take 30 minutes or more, and so forth. There's a variety of needs, and those needs continuously change. If I'm at work, I might need 30 minutes to finish my task, drive home and shelter with my family. When I'm on the road heading home, I might only need 15 minutes, and once I'm home, I might just need 5 minutes. So even my own need might continuously change. So if you provide a message that provides 5-minute lead time, well, these are the needs that you meet and not the others. With a 20-minute lead time, you meet these needs and not the others. With 45 minutes and so forth. So I suggest that lead time really relates to the customizability of warning information to meet a variety of different needs. The longer lead time you can provide, the more needs ultimately you can meet. Here's an example of a tornado warning. This one actually has a pathcast, and you can see the lead times range from 5 or 6 minutes for the first town or two to 45, 50 minutes for the latter towns. Warning itself is not a tool that can provide customizable threat information. So as you see in this example, it provides one precautionary statement for everybody. Take cover now, which is appropriate for towns that are 5 or 10 minutes away from the storm. But for people 30 to 45 minutes away, unlikely they're going to take cover for that long a period of time. So the reality is there's no one size that fits all here. Different people have different needs, and those needs can continuously change. An interesting question that arises is, does the necessary lead time have to come from a warning? As you know, our agency is evolving from being product-focused to being service-focused, with a focus more on DSS messaging. This is a big deal when it comes to achieving greatness in high-impact weather operations, particularly in a world where automation is becoming more and more prevalent. So I'm going to turn now to focusing on DSS threat messaging. There are good aspects to automation, such as reduced workload, greater information flow, greater operational efficiency. But there are undesirable aspects as well, such as reduced opportunity to achieve greatness in operations. And the NVM is an example. It's a great forecasting resource for providing efficient steps to generate the forecast on all the products that we issue. But over-reliance on it and not making the effort to QC the output and incorporate science can sometimes lead to bad results, particularly in more extreme patterns. Here's an example of a freak winter storm, and I mean freak, as it really shouldn't have happened, and usually doesn't given our close proximity to the Gulf of Mexico. Northeast Florida and southeast Georgia get a winter storm about once every 30 years, primarily on the backside of a developing Atlantic extratropical cyclone where we have cold advection and rain turns over to sleet or snow before ending. That was the case just over 30 years ago, around Christmas of 1989. But for this system in early 2018, it was different. It was an intense open wave coming in from the west and leading to a warm advection pattern over a initially cool dry air mass. Given how close the Gulf of Mexico is, almost always leads to a rapid changeover of any winter precipitation to rain as temperatures rise through the 30s. But that was not the case in this event. Temperatures changed very little. And that was due to very intense lift along a deformation zone. And you need that lift. You need very strong isentropic lift to cause enough cooling to balance the warming due to advection and lead to little change in the vertical thermal profile. And that was the case here, and the precipitation stayed in the form of ice and snow. You also had to know things like limiting streamlines and the impact of the streamline between the flow along cold, dry land and the streamline flow from the warm, moist Atlantic. And that limiting streamline between the two was the eastern edge of the accumulating winter precip. So being able to produce a precise warning that matched exactly where the impacts would be and not covering areas like our biggest population area in Jacksonville where there would not be significant impacts and thus life could go on as normal, that requires knowledge and experience and being able to understand NWP, which in this case was terrible. Most of the models were wrong, either showing no precipitation over the colder air or showing a rapid changeover to rain. I believe the NAM was the best of them all with a later changeover, but still an eventual changeover from freezing rain to liquid rain. So knowledge and experience are critical for knowing when the models may be right or wrong and knowing how to make proper adjustments to model guidance. Automation also sometimes leads to bad end results. If there's no QCing, for example. Here's an example of an observation from our website for an airport during a calm, foggy morning, except that here the winds were Cat 5 hurricane level. Likely bad data that was not QC'd before release of the observation. So there's quite a bit of automation now in the warning process as far as the warning product. WarnGen automates a lot of what is generated once you draw the polygon and create your product. It does not allow the kind of customizable threat information that other tools, such as DSS threat messaging, might provide. So as one door closes through automation, perhaps another door opens. Our flagship products from the WFO and hazardous weather operations are the watch and the warning. But in fact, we could provide a range of lead time information through different efforts, with DSS playing a key role. So we have our flagship warning product that provides anywhere from 5 to 45 minute lead times. Its main benefit is the alert feature that is not provided in any of the other products that we offer other than watches. But its automated approach to the information it provides does not allow really good preciseness and customization of information for a given location. That's where DSS targeting could come into play by providing updates of where hazards are in particular and where they're going, particularly in the 5 to 10 minute lead time period when we want people to take immediate protective action, where DSS could be very beneficial in targeting the exact area where we want that to occur. DSS messaging can also be beneficial ahead of the warning, up to 1 or 2 hours in advance of the hazard. This is something we really haven't tackled much in the Weather Service, but it can be very beneficial for people who have longer lead time decisions to make, such as people who are at work who may want to finish a task and then drive home to take shelter with family. So this sets up kind of the ready, set, go approach in high impact operations. In the Outlook time frame, and we're looking 8, 12 hours ahead of an event, there is skill in forecasting where severe weather will occur and where it won't occur. But the skill for precisely forecasting coverage is much less because a lot of things change over that 8 to 12 hour period. And so much more often than not, we may get an end result like we see in the lower left, with a large slight risk area, but the end result might be some clusters of severe weather that could be enhanced risk type coverage, along with large areas where no severe weather occurs at all. As we get to an hour or two ahead of the event, we have the tools and technology to try and recognize environment changes, where convective initiation is more likely to occur, how the instability is evolving, and so forth, to be able to provide targeted threat messaging of where severe weather is likely to occur, as well as where it's likely not to occur, given how the environment has evolved. Here's an example from March 31st of 2020, and we're focusing on the Jacksonville CWA. You see a slight risk area across southern Georgia and a narrow marginal risk area across the I-10 corridor far in northern Florida. Early in this event, it was producing severe weather across southern Alabama and southwestern Georgia. As the convective system shifted east, however, the severe weather suddenly ended across Georgia. There was no severe weather in the Georgia part of Jacksonville CWA. The severe weather shifted south to the marginal risk area along the I-10 corridor, where we had numerous reports of wind and some reports of tornadoes. Could we have communicated that ahead of the event to know where severe weather would occur and where it likely would not occur? If we looked at the key ingredients for severe weather as it set up, as it was moving over the Jacksonville CWA, the surface-based instability laid out like this, mainly over the Florida Peninsula, with more elevated instability further north across southern Georgia, where we had more widespread rainfall. The shear that was favorable for severe storms was aligned like this, ahead of an intense upper system, basically the I-10 corridor northward, with shear decreasing as you move southward across the peninsula. And then as we looked at lift, it was very similar, with the lift associated with that system and with related boundaries, mainly from the I-10 corridor northward, with very little impetus for lift further south. So where do these key ingredients overlap? Right along the I-10 corridor. Early on, they overlapped across southern Alabama and southwest Georgia, where severe weather occurred. But as the convective system evolved eastward, we had widespread stratiform rain develop across southern Georgia that led to more elevated instability, with the more intense convection developing along the southern periphery of the convective system that's tracked across the I-10 corridor. We have tools that we could use to communicate this, where we think severe weather is likely to occur or not occur 1 to 2 hours ahead of a potential event. How about during the hazard itself? Here we have an example of a tornadic storm in Oklahoma. With every radar scan, we know where the tornado is, within a few square miles. Maybe not perfectly because the data are not perfect, but within a few square miles of Moore, Oklahoma, we know there's likely a tornado ongoing here. And it's tracking to the northeast. So from that, we know that Tinker Air Force Base is in the direct path of the storm. And we can communicate that. Now, in the past, way back when I was a forecaster, back before we had WarnGen and we had to manually type forecasts and warnings, we had the ability to type one-line SVSs to indicate here's where the tornado is, here's where it's going after every radar scan. Some offices utilized weather radio quite geniusly by having live play-by-play broadcasting, again indicating the where and the when and who is directly impacted. Well, with automation, obviously, we have WarnGen, and weather radio has also been automated, but new opportunities have evolved with DSS messaging through NWS chat and social media to provide quick information after each radar scan of where the threat is and where it's going and who's going to be directly impacted. So now I need to try and relate DSS messaging to the need to manage risk, because again, to achieve greatness, you have to accept greater risk and you have to make greater effort to deal with that risk. So let's see how DSS messaging relates to that. So I'm going to briefly refer to risk management, and this comes from a module in the Mesoscale Environment Analysis course. Risk, when we talk about risk, we're referring to both uncertainty and consequences. Risk goes up when either of these two go up. So when we refer to risk management or managing risk, we're talking about applying policies, practices, and procedures to identify, analyze, assess, treat, and monitor risk. Let's think about life and what it would be like without risk management. How could insurance companies provide policies? And how could banks offer loans given the risk of defaults? How could airlines fly planes given the risk of, crashes? How could police and fire officials operate during emergencies given risks to their safety? So these are just some examples where risk management is important, and it's for almost anything. One option we have is to minimize risk. But how would that benefit anyone? Remember, when you minimize risk, you minimize reward. So in minimizing risk, we would have very few insurance policies and very few bank loans offered, only to the most secure people. We'd have very few flights due to the risk of crashes, and probably minimal response to emergencies due to the risk to the safety of police and fire officials. So risk minimization is not a good approach. We need an approach in which we can smartly manage risk, recognize it exists, but manage it in a way that allows us to still try to achieve greatness in operations. And for that, we're going to focus on 3 actions: increasing knowledge and experience, incorporating better science into operations, and recognizing potential consequences and accounting for that. So a key part of managing risk is education. And in the past, it's been focused on radar, but now we have a new course, the Mesoscale Environment Analysis course, that goes more in detail about storm and environment, and using that to anticipate what the radar is going to show to provide longer lead time, as well as to utilize this to message the potential for hazards even before warnings are needed. It has a variety of sections. It has information on tools and technologies for mesoanalysis. It has information on targeting specific hazards and on risk management, as well as MIA communication, internally and externally. It also comes with exercises for building experience in mesoanalysis. So how important is this type of training? How much of this training do we need to complete it before we can incorporate mesoanalysis into operations? Is half of the course sufficient? Well, that leads to a different question, but related. If you're on an airplane and you have a young flight crew like this that has completed half of their training, and mostly on Cessnas, but now they're going to be flying a Boeing 737, would you stay on the plane? So I wouldn't. I'd be off that plane in an instant. I would want a captain who has not only completed full training, but also has years of experience under his belt as well. The same likely applies to an ambulance crew who arrives at the scene to help someone who is not breathing. They come and they say they have not had CPR training in the last year or 2, but they'll do their best. That's not exactly what you want to help the person in need. You want someone who's fully experienced and fully educated. In the WFO, perhaps the most beneficial yet most underutilized tool is the Weather Event Simulator. We utilize it to go through past cases and gain some experience in warning decision making. But there's another benefit to this tool that we don't really take advantage of, and we see it with how airline pilots utilize simulators. Now, they use it in the same way as far as building flight time. It's cheaper to do it this way than through actual aircraft. So they use it to build experience much as we use simulators. But they also utilize them to gain practice in dealing with crises. It might be loss of an engine during a flight, loss of electrical power. Maybe the landing gear fails to come down before landing. Or as you're about to land, there's an aircraft on your runway and you have to abort quickly. Or you have to take off or land in a microburst. In these type of crises, they can go through simulations of these over and over and over again, so that should they face one of these crises in an actual flight, there's no fear. They know exactly what to do. They've practiced it. They know what actions to take. We don't utilize that in the Weather Service. We don't have a national program to put all forecasters through past failures over and over and over again to highlight corrective actions to take to prevent failures in the future. As a result, I've seen the same mistakes today as I've seen 10 or 15 years ago, and they'll likely be made again in the future because we don't learn from the mistakes of the past and thus are doomed to repeat them. Have you tried completing a simulation with no radar data as a means to assess the impact of fear on your decision making? I used to do this early on in my SU days in creating simulations. I'd delete several radar scans to simulate a radar outage to see if that made a difference in the decisions one makes. Theoretically, given all the data and technologies we have today, it should make a huge difference because we have, for example, lightning data that can indicate where the deeper cores are. We have satellite information and so forth. And you can utilize other information from distant radars. It should make a huge difference. It's not the most ideal situation, but it shouldn't negatively impact you in a substantial way. So a key value of the WES is having the ability to repeatedly practice failure scenarios as well as to build operational experience. R2O, Research to Operations, is a key process for incorporating better science into operations. And that's an important step for trying to control the impact of fear by having better knowledge of what's going on in the environment and what that will support, what the radar should eventually show in the future. So science is an important step in risk management. Trying to better understand, for example, how this sounding relates to what the storm intensity will be. What impact will that layer of dry air have? The white dashed line is a pseudo-moist adiabat that is related to the updraft, but that assumes no mixing whatsoever. If there is mixing of this dry air, the actual updraft curve might be more like that, yielding a shorter storm and maybe even a weaker updraft overall. On that particular topic, let's do a quick home experiment. And I'm going to use my favorite laboratory, the kitchen. Okay, here we are in the kitchen, and I have a pot of rapidly boiling water on the stove. You can see the steam rapidly rising up, and this is going to be our cumulonimbus cloud, if you will. So, there are two signs that mixing plays a key role here in terms of what's going on. The first is that you see a lot of the steam rising quickly above the hot boiling water, but as you get up to about this height here, the steam starts to disappear. And that's likely due to evaporation. There's a lot of cooler, drier air up here that's mixing in with the hot, steamy water vapor, causing evaporation. The second sign I'm going to show you is this. I'm going to put my hand over the pot of water, a few inches above the pot. If mixing occurs, there should be enough cooler air particles here mixing with the steamy air that will result in the air feeling warm to my hand, but I should not burn myself. Now, if mixing doesn't occur, we could have a much uglier end result. So here we go. 1, 2, 3. Wait, time out. Let's think about this for a moment. Make sure we're on the same page here. If I were wrong and I burned myself severely, do you think I would actually share that part of the video with you? Or would I cut that part out and share the rest with you? So, just so we're clear, let's go back to the experiment. Okay, so here we go. 1, 2, 3. So it feels warm. It definitely feels warm to me, but it's not scalding hot. And that's because of mixing, thankfully. So there's enough cool air mixing with the steamy particles that my hand will feel warm, but I'm not being burned. Now, if I put my hand down near the surface of the water, likely a very different and uglier result. So part of risk is the potential for consequences if something bad happens. And that can vary. For example, a storm that tracks along the red arrow over a high population area of Jacksonville, Florida, has a greater potential for consequences if something bad happens than for a storm tracking along the magenta arrow over the swamp where no people live. Now, the level of risk also relates to the amount of data you have available. For Jacksonville, we have a lot of radar data due to a nearby radar along with a lot of surface observations. But compare that to a storm tracking along the blue arrow over another big population center where we have no radar data below 8,000 or 9,000 feet and very few surface observations. The risk for something to be missed is even greater along the blue arrow. And as such, adjustments have to be made to account for the potential for consequences. So to summarize this video, I'd like to go back to this graphic that again relates achievement to the level of satisfaction and fulfillment that you can get from that achievement. It also relates to the risk of failure. You cannot have a substantial reward without encountering substantial risk. And it also relates directly to the amount of effort and the difficulty of the effort required to manage that risk. For example, mesoanalysis takes a lot of effort so that you better understand storm environment and can better interpret what the radar is showing and what is likely to occur. It is through risk management efforts that we can achieve greatness while keeping risk in check. So think about what action specifically we can take to do so. When you have a warning for a county, what can you message to the next downstream county or two, and when do you do so? Think about DSS messaging. On radar, you know where a tornado likely is located within a few square miles during every scan. How can you communicate that prime of precise information on what you know and what's going to occur and where the threat is and where it will not be. Again, consider DSS messaging. How can you downscale a threat message ahead of warnings with an hour or 2 hours lead time to prepare a community for a potential incoming threat? Consider DSS messaging. How can you provide better information, more specific, more precise, more accurate to a larger audience? Think of NWS Chat to core partners and the audience they have, as well as social media. Again, DSS messaging. What tool provides the best when it comes to alerting the public of a product? For that, warnings are at the top, and that is what makes warnings the numero uno product of the Weather Service, because of that alert feature that other products, except for watches, other products don't have. How about, however, providing specific threat and response information, being able to precisely show who needs to take immediate action and who does not? In that aspect, consider DSS messaging. So our future is focused on DSS and on targeted threat messaging. This is the tool, in my opinion, that supports greatness and high impact operations in the future. This is the tool that we evolve to manage risk that is associated with warnings while providing the kind of information people need to make the variety of decisions they make. Greatness in operations simply cannot be achieved through radar-based warnings alone. Simply making decisions based on radar signatures is more along the lines of satisfactoriness, meeting the mission and nothing else. Greatness can be achieved through targeted threat messaging ahead of the threat, as well as more precise, action-focused messaging during the threat. I hope this video has been beneficial in demonstrating the value of DSS threat information when it comes to achieving greatness in high-impact weather operations. It's my key argument as to why I believe DSS threat messaging is rising above warnings in terms of priority, given the ability to communicate very precise threat information that supports protective action. Recall that 10 square mile warning area I talked about earlier. Impossible to do with WarnGen, but with DSS threat messaging, we can communicate information to that scale with each radar scan. In addition, we can communicate threat information beyond the warning period, which we haven't really done much of in the past. And it is that type of effort that really helps achieve greatness and the underlying satisfaction and fulfillment that comes from it. Thanks for watching.